Hello everyone. Today we'll discuss simple harmonic motion. Our objectives are define simple harmonic motion, or SHM, describe the properties of an oscillator, SHO, that's simple harmonic oscillator, define amplitude, frequency, and period, describe the relationship between speed, amplitude, and displacement, apply energy considerations, and derive an equation for maximum speed in simple harmonic motion. And our goal is to do this in 20 minutes or less. Simple harmonic motion, it's a very important topic in physics because you will encounter, if you decide to pursue anything in STEM and have to do in physics, in many branches of physics. You can find it in quantum mechanics, you can find it in cosmology, thermodynamics, so it is everywhere. And we can model a lot of things in the universe with simple harmonic motion. So there are obvious things such as a pendulum. You guys used a pendulum for your lab, right? So if we pick an amplitude and we just let it swing. And you might think, okay, so this is a school thing, maybe. But if you think about it, we have clocks, old clocks that work in this fashion. Think of Spider-Man. He uses oscillatory motion, kind of like this. Someone on a swing. So we can model a lot of things using this type of motion. Furthermore, if we increase the scale of things, we can model the motion of our solar system using simple harmonic motion. Other things like plugging a string on a guitar, playing the violin, all those things can be modeled with periodic motion. And before we define what simple harmonic motion is, we have to establish some vocabulary that's going to help us to better understand simple harmonic motion. Let us start with periodic motion, because I've thrown that word repeatedly, and in case you don't know what it means, here it goes. It is motion that repeats itself at regular time intervals. For instance, your heart rate, your palpitations can be modeled with simple harmonic motion. Next is period. Period is the time to complete one oscillation, that is moving back and forth from start to end, back and forth, to and fro, or one cycle. And notice that we have time, therefore we can estimate, we can assume that the units are seconds, and the symbol for period is going to be capital T. Now, let's define frequency. It is the number of events per unit time. And the symbol is lowercase f. For instance, if you work, chances are that you get paid bi-weekly. So the frequency at which you get paid is every 2 weeks. Number of events per unit time. You get one paycheck per 2 weeks. So now let's define the mathematical relationship between period and frequency, which is rather simple. Frequency is equal to 1 divided by the period. Likewise, the period is equal to 1 divided by the frequency. And let's define the units for frequency, because we already know that the units for period are seconds, because it is the time required to complete one cycle or one oscillation. So let's start with the formula. Frequency is 1 over period. We know the unit for period is second. So therefore, the unit for frequency is 1 over second, or some textbooks have it as second to the negative 1. But the most common, I think, is hertz. This is 1 Hz, and that's an abbreviation for hertz. For instance, if we have a 2, so if it takes 2 seconds to complete one oscillation, then the frequency is going to be 0.5 hertz. And this has no relationship whatsoever to the car rental place. It's after a scientist. Okay, so these are the units for hertz. And just so we don't forget, let's remind ourselves that the units for period are seconds. And the symbol is lowercase s, as usual. Okay, so now that we have these defined, we can define what simple harmonic motion is. Simple harmonic motion can be defined as the oscillatory motion, repetitive cyclical motion, for a system where the net force can be described by Hooke's law. Such system is called a simple harmonic oscillator. And we haven't learned what Hooke's law is, although we used it for the previous homework. I don't know why, but I digress. And it is very simple, okay? Very, very simple. So the oscillator is going to be the object that is moving back and forth, oscillating. It could be the pendulum, it could be mass in a spring, it could be a planet, anything that is showing oscillatory, repetitive, cyclical motion. So let's find what Hooke's law is. And it's super simple, and it's after physicist Robert Hooke. And it says the following. F is equal to negative kx. This is restoring force is equal to negative force constant times displacement. Let's try what these are. Okay, now let's talk about the negative sign. The negative sign tells you that the direction of the restoring force is always opposite to the direction of the displacement. Let me explain. So I have this object here. It is called a straight edge. Because I taught geometry, I learned that rulers are dictators or overlords, and these things are called straight edge or straight edges. But I digress. So when the straight edge is not moving, just in my hand, it is at its equilibrium position. So then I apply a force by pulling to the right. Then Hooke's law tells me that the straight edge is going to experience a restoring force intrinsic of the object, and it's going to make the object move to the left, and then once it's to the left, it's going to move to the right until it reaches its equilibrium position, which is its resting position. The same thing happens with the pendulum, right? Eventually the pendulum stops at its equilibrium position, mass in a spring, same thing. Oh, one more thing. K is the force constant. Some textbooks have it as the spring constant, but not everything's a spring, although you can model everything, almost everything, as a mass in a spring. But not everything's a spring, so I like to call it force constant, but it means the same thing. If you have a spring, then that constant is simply the stiffness of the spring. Okay, so I think the most intuitive way to learn simple harmonic motion, restoring forces, and Hooke's law is via the mass or a mass on a spring system. And I have this apparatus which will illustrate simple harmonic motion. So as you can see, I am not doing anything to the mass on the spring. It's resting. I'm about to move it. Right now it's at its resting position. It's a little under 6 centimeters. Now let's define what amplitude is in a harmonic oscillator in simple harmonic motion. So amplitude is the maximum displacement from the equilibrium position. For instance, if I go back to the pendulum, maybe you guys remember this from your lab, the amplitude is simply the degree that I pick. So let's go for 20 degrees. And then I release the pendulum. So the amplitude is the maximum displacement. In this case, the displacement is measured in degrees, so it should have the theta there. But the better way, I think, to understand amplitude is by the mass on a spring. So here's a video that shows a mass on a spring oscillating. As you can see, I pull down at around 9 centimeters. So the displacement, the maximum displacement or the amplitude would be 0.03 meters or 3 centimeters. That would be the maximum displacement or its amplitude. So amplitude is usually a term used in waves, the amplitude of a wave, and mass on a spring shows oscillatory motion, and then we trace that, we can have a wave. So waves and simple harmonic motion are connected, although we're not going to study that today. And then you saw it when I graphed the motion, right? You saw a wave. And this wave is a very special one. If we were to solve Hooke's law using more advanced physics concepts, we would end up with an equation of motion that would describe the position of this mass on a spring at any time, and it uses the sine wave. These waves are called sinusoidal waves. If you are taking pre-cal, you learn about those type of waves. So now, what if we want to learn about the relationship between amplitude and speed? Okay, because now we know that amplitude and displacement are connected. So as you can see on the video, the motion is repetitive, cyclical, oscillatory. And let's think of the maximum displacement or the amplitude. Well, the amplitude happens when I pull down the spring. It is at around 0.03, 0.03 as you can see is shown here. Okay, so now let's go for the positive, right? The positive right here, at 0.3. At that amplitude, at the maximum displacement, let's see what is the velocity. Now I know the formula for Hooke's law has an x. Here we're going to look at the y direction. That's because I set up my coordinate system, so up and down is the y. Okay, so when the y is at 0.03, the velocity is at 0. And that's a very important fact of simple harmonic motion. And I think it's harder for anyone to see with the pendulum, but with the mass on a spring, when you analyze the motion, you can see that when the displacement is at its maximum, when we have the amplitude of the wave that is traced or that is formed, the velocity is 0. Therefore, we can say at maximum displacement, the speed of the oscillator is 0. Now let's think of what happens when the speed is at its maximum. So now we have to look at the y velocity, and when is it that it reaches its maximum speed. So I know 0.12 is here, but that's more of an outlier. The one that will repeat the most is 0.1, but even at 0.12 we can see, okay? So let's see at 0.12, what is the displacement? 0.007, which is very, very short, or if we just use 0.1 because that's the one that repeats the most for maximum speed, then we can see that the displacement is 0. So then, if you look at the mass on a spring, well, when the mass on a spring reaches or goes through or passes by the equilibrium position, right, when the displacement is 0, the maximum speed is reached. So maximum speed is reached when we have 0 displacement. If you think about it, the relationship is reversed. At maximum speed, displacement is 0. So we can formalize this mathematically, sort of, in the following manner. Maximum displacement corresponds to 0 velocity, And maximum speed, so I should be saying speed, maximum speed corresponds to 0 displacement. And this applies to any object, any system that is being modeled as a harmonic oscillator, pendulum, planet, particle vibrating, whatever. This holds true. Okay, why is this important? Well, that's because we can now apply energy considerations and derive more properties of oscillators. Let's look at the video again for the mass on a spring. As you can see, when I'm pulling down the mass, I am doing work on the system and increasing its energy, okay? And the energy right before I release is all potential, not gravitational potential energy, although that it's involved in a way, but we can just say it is elastic potential energy. And we learned this formula in Unit 3, and it said that the potential energy on a spring, elastic potential energy, is 1/2 kx squared. K is the force constant and x is, as we established, displacement. Okay, now let's think about the motion again. When I'm pulling down to its maximum displacement, right before I release, if we were to measure the energy of the system at that point, well, that would be its maximum, its total energy. So we can start with the regular energy conservation relationship. The total energy of the system is going to be a combination of kinetic energy and elastic potential energy, okay? But now the total energy is based on the displacement, the amplitude I give this mass in a spring as I pull it down. Therefore, the total energy is elastic potential energy when the displacement is maximum. And we said that the maximum displacement is the amplitude, or A. Therefore, we can rewrite this formula as 1/2 Ka squared. Now, we can substitute this here and then write the typical traditional equations we know for kinetic energy and elastic potential energy as follows. And then you might be saying, can't we cancel the 1/2? Yes, we can, of course. But I want to leave it like that because this shows energy conservation for a mass on a spring or a harmonic oscillator, where V is the speed of the oscillator, in this case the mass on the spring, X is displacement, K is the force constant, A is amplitude. Okay, now let's apply these situations. Okay, what if we wanted to know the maximum speed of the mass on the spring? Well, we know that the maximum speed happens or corresponds to a displacement of 0. Therefore, when I write this down, this term cancels because I would plug in 0 here, and this whole term, the elastic potential energy, when the mass on a spring is at its maximum speed, is 0. Now this I'm going to leave as it is because this is the total energy, and we know energy is conserved, which means we'll have the following. So the maximum kinetic energy corresponds to the maximum speed, which in turn corresponds to the total energy based on the amplitude. Now let's solve for maximum speed for V max. Of course, we're going to cancel the 1/2. And then I'm going to use the reflexive property, which means I'm going to have this on the left and this on the right. We're going to divide by the mass. And then we'll take the square root on both sides. Notice that the square root will cancel this square and the square for the amplitude. Therefore, I'm going to write the right side splitting K over M in A squared. So the maximum speed is the square root of K over M times the amplitude. This here, this term over here, is very important, and it has its own name. The square root of k over m is known as the angular frequency, and the symbol is omega naught. Now this omega is somewhat related to the omega we used in Unit 5, angular speed, and I included a video on the description wherein I go a little bit more in depth on how or why omega naught is related to the angular speed, but this is called angular frequency. And it's a very, very important quantity in simple harmonic motion. So now what we'll do is, well, let's solve for k and write our energy conservation using angular frequency. So to solve for k, we'll do the following. I squared both sides, then I'm going to multiply times the mass. And the force constant is equal to angular frequency squared times the mass. So now let's write our energy conservation relationship using angular frequency. Here we have it. Now we have angular frequency repeated on both on the left and the right. And I know you can see we're going to be able to cancel the mass, but I'm not going to go into that. We have two more quantities that I want to go over. And I'm not going to derive those quantities. I just want you to have those formulas, okay? So the period of a mass in a spring, or if we're modeling in a system as a mass in a spring, the period will be as follows. 2 pi times the square root of m over k. And notice how this is flipped. So we can say that the period is equal to 2 pi divided by omega naught by the angular frequency. And because we know period is equal to 1 divided by the frequency, then the frequency is going to be 1 over 2 pi times k over m. We know that, times the square root of k over m. And we know that k over m is omega naught. So there we have it. Period and frequency of a harmonic oscillator. And that's it.